Hi everyone, welcome to our final demo. We're the Blocks Code version 3 team. Our project is a physical block-based programming system where you literally snap magnetic blocks together to build a program. There's no keyboard, no traditional IDE. The physical arrangement of blocks is the code.
Programming is powerful, but for beginners, it's very abstract. You're starting on an empty text editor, there's no physical feedback, and concepts like loops or branches are invisible. It's easy to get stuck before you even see something real happen. Our goal for this semester was to make programming tangible. You build your program as a chain of physical blocks. The brain reads that arrangement, checks that it is valid, program, and then executes it with real LEDs, audio, and touch display, all in real time.
For requirements, we focused on 3 big ideas. First, functionally, the system has to detect which blocks are connected and in what order, validate that sequence against our syntax rules, and then execute on command, driving LEDs, audio, and the display with real-time feedback in the companion app. Secondly, on the engineering side, we defined 3 quantitative specs that we'll show today. LED color preview latency under 50 milliseconds, config change to app latency under 2 seconds, and I2C rise time under 1,000 nanoseconds. We will walk through the results of the specs later in the demo.
All 15 blocks share a common hardware platform. Each one has an ESP32 microcontroller, a TFT touch display, an LED matrix, addressable LEDs, and an audio path with an amplifier and speaker, all powered through rechargeable lithium-ion batteries. At the system level, we have 1 brain block and 14 child blocks. The brain is the I2C master and runs the program executor. The child blocks are all identical from a hardware perspective, but they present themselves as different logical block types over I2C.
Those logical types fall into 3 main categories. We have control flow blocks, if, then, and if, loop, and delay, which shapes the structure of the program, but don't directly produce output. We have a single input block, a button press block, which gives us user interaction for if statements. And we also have output blocks, like LED color flash, note, and music sequence. From the user's point of view, you snap a chain together, tap the TFT on each block to configure its behavior, and the LEDs and speaker give immediate visual and audio feedback.
This is the full architecture. On the left, all of the child blocks share a single I2C bus. The brain block in the middle acts as the I2C master, runs a config manager to scan and identify the current topology, and has an executor plus a TCP client running on the ESP32. On the right is our Flutter companion app. It runs a TCP server on a fixed port, receives JSON block config messages from the brain, parses those into a Dart model, validates the program according to our grammar rules, and then updates the UI in real time, showing the block list, any errors, and a 3D view of the configuration. Physically, all of this rides on 1 I2C bus running at 100 kHz with addresses allocated across the brain and child blocks.
Zooming in on the brain, it continuously scans I2C addresses from 8 to 16 using a dedicated scan task. For each address that responds, it reads a Who Am I register to learn what logical block type is present. The config manager compares the new scan to the previous one to detect adds, removes, or type changes, and when something changes, it builds a JSON block config structure and caches that under a mutex. That chain sets an event bit that wakes the TCP client task, which then streams the most recent JSON up to the app. From there, the brain can send commands down to the blocks, ping, set LED, execute, reset, and so on, so it fully controls execution over I2C.
On the app side, every time we get a new JSON configuration, we run it through a validation engine. We enforce 4 rules. 1. The brain must exist and be at index 0. 2. If blocks must be followed by a button, then, some outputs, and an end if. 3. Loops must start at loop and end at end loop with only output blocks inside, and we warn on interleaved or overlapping structures since they are pretty complicated. You can see examples on this slide: a valid loop sequence, an if without an end if that is rejected, and a correct if with button and then. The app surfaces all of that in the UI, so if the physical chain is invalid, we show an error and we don't let you execute. Now we will transition into our live demonstrations. We have 4 scenarios to show you to prove the varied features of the blocks in the app. First, we will show you our interactive walkthrough tutorial, which guides the user through building an if-then sequence.
The Flutter app includes a guided walkthrough tutorial, which is vital for beginners. This tutorial guides the user through building an if statement sequence, representing user interactivity, step by step, validating their block connections in real time. Here in the app, the user enters the tutorial mode. It visually demonstrates which block they need to connect next, brain, if, and the button press block. As we snap the physical blocks together, the app dynamically acknowledges the placement when we execute. The brain pauses, waiting for that physical button press before proceeding to the then branch.
Single note. Submit. Okay, sorry. One hard. Okay. Now what? Press start on the line.
You'll see the button block now says press now.
Once pressed, the conditional is met and execution resumes. This proves our system can securely stream topology to the app while simultaneously handling complex blocking hardware input events.
Now let's look at the output blocks, the LED color flash, the note block, and the music sequence block. This demo will illustrate how all three outputs can be programmed. First, we connect the LED color flash block, input a color on the TFT, and it immediately previews. Next, we swap it for a note block. You select a specific frequency and duration on its display, and you'll hear the immediate audio preview. Finally, the music sequence block allows you to choose from a list of pre-programmed melodies. We snap the brain block on and execute a quick sequence. This confirms that our block hardware is correctly receiving commands over I2C to manipulate the WS2812 LEDs in the LM386 audio amplifier.
For our next demo, we'll demonstrate a control flow loop structure. We want a sequence of notes to repeat based on a count. First, we connect the brain to a loop block. We then connect up a note block and an end loop block. We will configure the note block to the sequence that we want and then configure the loop block's count to 3 times. The Flutter app acknowledges this is a valid loop sequence. When we tap execute, the brain iterates through the child blocks exactly 3 times. The state management in the brain's executor correctly maintains the program counter jump points for the loop structure.
Our ultimate functionality test is pushing the system to its maximum capacity, 1 brain and 14 functional child blocks on a single I2C bus. Here is the final configuration. It's a massive program. Brain, then loop, then note, then LED, then end loop, then delay, then music 1, then music 2, then if, then bottom, then note, then note, then LED, then end if. Watch as the Flutter app correctly identifies all 15 blocks. We press execute and the brain effortlessly delegates the entire complex control flow and audiovisual sequence. Twice, delay.
Now we will review the engineering specifications that validate the performance of the system behind the scenes.
Spec 1 measured LED touch to preview latency, evaluating UX responsiveness. The target is under 50 milliseconds. We use a logic analyzer to measure the time delta between the SPI touch event and the WS2812 output pin transition. Our testing across 10 runs produced a mean of 13.1 milliseconds. We comfortably meet Spec 1. Spec 2 measures the end-to-end pipeline latency from physically adding a block to the app UI updating, targeting under 2,000 milliseconds. Out of 10 runs, our mean latency was approximately 50 milliseconds, passing this requirement easily.
Spec 3 evaluates the electrical integrity of our shared communication bus. We measure the 30 to 70% rise time on the SL line. Crucially, we are measuring this under the absolute maximum bus load, with all 15 blocks connected, stressing the line capacitance. We are using an oscilloscope proving the shared I2C bus during full scan sequence. The cursors indicate the 30 to 70% rise time along the rising edge on the signal. Our target, keeping within standard I2C operating mode safety margins, was under 100 nanoseconds, with all 15 blocks connected and operating in standard mode I2C at 100 kHz. Our measurements comfortably meet this requirement. Across 10 runs, we measure a mean rise time of 425.57 nanoseconds, ensuring reliable data integrity even at maximum system load. Looking at the three representative captures shown, two measurements fall around 380 to 390 nanoseconds, while one is higher at approximately 764 nanoseconds. This higher value comes from address 10, which corresponds to the 14th block in the chain. We attribute this to increased capacitance near the end of the shared I2C bus, which shows the rising edge of the signal. Even in this worst-case condition, the rise time remains well within spec, so the system operates safely at full capacity.
So overall, all three specs passed and everything worked the way we wanted it to. After multiple runs, we were able to show that our system is fast, responsive, and stable, even with all blocks connected. To wrap up, we have successfully demonstrated the core of the blocks of code system, the 15 magnetic blocks, the complex conditional logic, the interactive outputs, and the responsive cross-platform application integrate seamlessly.
Our architecture safely handles massive configurations, the electrical buses operate within spec under full load, and beginners now have a tangible, immediate bridge to entering the programming world. As we look ahead, we're focused on deeper user testing, introducing advanced programming concepts like variables and logic operators or Boolean operators, and expanding the system with voice controls and new modular sensors. Thank you so much for listening. We're happy to take any questions.